So medium problem today. We have list of numbers. And we can make jumps from position if the previous value is bigger. So it's left up jump, and right down. So right down means we can jump to the smaller values, and left up means we can jump to the bigger values to the left. And they ask us to find the final form of all the jumps and make the maximum of the visited path. So from this example we can see that, for example, 1 can jump to 9 and became 9, 5 can jump to 1 and then jump to 9, so it's 9. 3 can jump to 1 and then jump to 9, and 2 can jump to 1 and jump to 9. So they all be 9s. Now this is one example, and the problem is kind of big, 10 to the power 5 items count, so it should be solved in O of n or n log n, except now let's think about how this can be solved. So the first idea is the forward pass. What can we do in one single forward pass? Imagine we have some numbers like this, 1, 2, 3, 1, 2, 3, and in a forward pass we can say that any value into the left that is bigger is overridden the current value. So 1, 2, 3 stays 1, 2, 3 because now left value is bigger, and then 1 becomes 3, 2 becomes 3 because it can jump to 3, and 3 stays 3, so it's kind of becomes running maximum. But this is only half of the problem, because it's not the guarantee of all the optimal examples. So imagine we have some example where we can jump to the right, then jump to the left, and then jump to the right again. So let's think about this, like 7, jump to the left like 5, and then jump to the right 5, and jump to the left. Okay. Somebody play with this. Okay, so jump to the left should be bigger, like 8. Jumping to the left, then maybe 1. It can't jump anything, so it can't jump to the right. Maybe like 3 can jump to the left. And 7 can jump to the right, to the 5, and 5 can jump to the 8. So it's kind of many jumps solution, so this is interesting. So 3 goes here to 7, 7 goes to the 5 to the right, and 5 goes to the 8 to the left. So 3 becomes connected to 8. So this is interesting. And if we just do this one forward pass, we can do it like 1 7 7 8 8, but the 7 should be 8 because it was an extra jump. So now you can see the problem hardness. It's not that just a random sum. You have to do this kind of extra variation. It's not obvious, and it wasn't obvious for me, that you can do this in just 2 passes, but it's still worth to try it. Now, the forward pass, obviously, second pass is backwards. Now we should get from it as much as possible. What can we do from backward pass? So imagine we add 8 value. In the backward pass, we can definitely say that 8 can jump to 5 because 5 was visited. Okay, let's remember it. Now, when we see the 3, for example, what can we say? We can't say anything because 3 can't jump to the right at all. Now, but we have to just remember 3 because it can be useful for somebody, because our 5 is kind of big value compared to 3, so some value to the left can actually be bigger than 3 but smaller than 5. So for example 4, if we have 4, we can say that this 4 is awaiting for this 3 to be in the array, because this 3 is helpful for its jumps, and it can't jump to 5 because 5 is bigger, and we only can jump right down and left up. So this is our jumps. So now the idea came to my mind is that we have to remember values. Now we have to look at exactly what we have to remember, because 5 is useful because it is rightmost value. 3 is useful because it is smallest value. But what about 8? Is it useful? You can say that some value would be bigger than 8 to the left of it, but we can see that we have 5, and 5 is strategically in a better position because it is right of 8. So we don't want to remember 8, it is useless. So that means our final strategy is to store this kind of 5, then 3, and then maybe 1, and this is decreasing here, or okay, this is a monotonic decreasing, decreasing Q or Q. Okay, so this is non-pattern, and for each position, each value, we have to store positions. So this would be position sum 0, this would be like 4, this would be 6, I don't know, is it right or not, it doesn't matter. So now we have this helper storage, and we can use it. So for each position, like this 7 for example, we want to ask how far we can go with this stored visit values. So for example 5 is less than 7, that means we can go as far as 5 position, and this index is 6. And then we can say that previously in the 6th position we already have our running maximum, and it will be 8. So that means at 7 we can place 8, and this would be the solution. Let's talk about how we can find this. So we have sorted monotonic decreasing. It is sorted order. That means we can do binary search. So the final solution O of n log n. It doesn't require for any mathematical intuition. It doesn't require for any extra Africa moment, aha moments. No requirements for the cleverness of the brain. But I can show you. Let's look at the code. So this was my accepted code, accepted solution. This is our first iteration for the running maximum, and second backwards iteration. I tried to find with the binary search the value that is smaller. I kind of used debugging to make this code correct, and then I just use res equal res of this point. So I have to store values and pointers in separate arrays, and I place them if the monotonic property is holding. And now let's look at the more interesting code. So the interesting code requires you to actually have some other intuition, and as you can see, it's very small, and this has to be explained and proved. Now I tried my best to do this. So imagine we have this code already written. So we even binary search, we just finding with binary search this 6th position from our 7. Okay, one property. So super intuition, it's not mine. The result is sorted. This is a property that can be proved, but I will try to make it a little bit more abstract. So imagine we have our running sum, and this is increasing order, so it goes with increasing order, and we are at place I, going backwards in the second pass, and the previous was I plus 1. This was the previous one, and we're looking back to find our best value, best index that has value less than current I. So our jumper, let's call him A. This is jumper A. Jumper. jumper man, and this previous was jumper man B. And as a previous step, he also looked back. Where is the best position that is less than B? And you can say that A is less than B because we place it in a result like this. A is less than B. That means B is bigger, and B looking far, so he can find a spot T, for example. This is the best spot. It has value T. Let's call this J, position and value T. And T is less than B. Now, what can we say about A? The A is smaller than B. That means A requires and can jump to this. Okay, if A can jump to T, okay, then B definitely can jump to T. So if A can jump to like C, for example, that means A less than C, and B also less than C. So the B is kind of have more power. And okay, maybe I'm a little bit not very precise here, because this intuition of the solution assumes that the final result is sorted. So let's look at the code. I don't know. So we having this minimum value so far, and we're updating it with current and value. And if we have current result bigger than minimum value we've seen so far, that means we definitely can jump from this position to the left and to the right, because n is less. Minimum is to the right. That means from I we can jump to the left with I and to the right where previous minimum was, at least. And then we do this kind of propagation of the previous position result. And the only thing we have to prove that this propagation with I equal with I plus 1 is allowed.